So now we're going to look at an example of how we're going to use Gauss's law to find the electric field. And we assume we have a sphere, assume that is a sphere with radius big R, and then we're going to take a Gaussian sphere inside of that of little r. And because of the symmetry of the sphere, we know that the electric field is radially outward, and so is dA. So we can say that phi E equals integral of E vector dotted with dA vector, which is the same as E dA, sorry. And since they point in the same direction, that would be cosine of 0 degrees, or just 1. So this is the integral of E dA. So this is always going to be the same if E is parallel to dA. If it's anti-parallel, meaning pointing in the opposite direction, you can just have a minus sign somewhere. We have a uniform charged sphere, so that means E is uniform, which means that I can take the electric field outside of the integral, and if I integrate dA, I get A. And now I have a couple of things that I have to look at. Keep in mind that since the flux can also be the charge enclosed over epsilon naught, I need to know the charge enclosed for my Gaussian when I'm doing the inside part. So for our Gaussian surface, electric flux is the electric field, right, times the area of the Gaussian, surface area of the Gaussian, and that should be 4 pi times little r squared. And if we rearrange this, we can write this as 4 pi little r squared E. But it's also Qn over epsilon naught, so we can write that 4 pi little r squared E is the same as the charge inside over epsilon naught. And the charge inside is the charge density times the volume over epsilon naught. And the charge density is the entire charge over the entire volume. Notice this is capital R now. And then times the volume of the Gaussian, which is 4 pi, 4/3 pi, sorry, over little r cubed, all over epsilon naught. Notice that the 4 pi over 3 cancels from those things, leaving us with 4 pi r squared E equaling r little r cubed over big R cubed times Q over epsilon naught. So now we can say that E by itself is 1 over 4 pi r squared times r cubed over big R cubed Q over epsilon naught. And notice that little r's reduce, and I have 1 over 4 pi epsilon naught, 1 over 4 pi epsilon naught, little r over big R cubed times Q. But if you remember, we called this K in chapter 21. So I can say that the electric field is K Q R over R cubed. So inside the sphere, this would be the electric field. Also note that when big R equals little r, it implies that the electric field then is KQ. If I put a little r in for big R or a big R in little r, I should get something like this, which is a result we saw in the previous chapter. And lastly, if we draw a picture of this, we know we're going to peak at KQ over R squared. So as my little r is increasing, my electric field is going to increase, and then after a while it's going to reach the maximum at capital R, and then anything after that it will become smaller.